Thank you for the kind introduction, also for the invitation to speak here today. I'm going to say a few words about these projects that I've done, some of them more recently, some others are a little bit older, with people formerly at Oxford, Pratik, who moved recently to the US, and Michael Nee, who was a PhD student there, and now is a postdoc. And also with Timo, who you all know and might be in the audience. And if I have time, I will also say a few words about something which is currently ongoing. I guess I don't need to say it, but if there are questions or comments, please, you can stop me at any point. Good. So, yeah, before going to the real part of the talk, I want to show you this slide, which I believe summarizes the things that I want to say here today, and is the following. So let's be very optimistic. Let's imagine we find an axion tomorrow. And with this, I mean a point in this parameter space. This is just a cartoon, of course, but here we have GA gamma, the coupling to photons, versus the axion mass. So let's do this exercise. We imagine we find a point in this parameter space in one of the many existing experiments. And then the question is, what can we learn? Of course, you can start asking the usual and very interesting questions like, is this guy dark matter, or does it solve the strong CP problem? That means, is this the QCD axion? So by the end of the talk, I want to convince you that axions are, in addition, unique messengers to obtain or to give us, to provide information about the UV limit of the standard model. And I will show you how finding a light axion, by light, I will specify what I mean by light later, can rule out, can actually test some very well motivated UV theories, such as grand unification in 4 dimensions or in higher dimensions, like the so-called orbifold GATS. Also can test the perturbative heterotic string. And finally, and this is work in progress, can also say something about F-theory GATS. Good. So to be more concrete, what I mean by light axion in this context, a perfect example, the ideal candidate would be to observe axion-induced cosmic birefringence. So in case you're not familiar with this, if you have a very, very light, ultra-light axion, by light I mean lighter than Hubble recombination, that couples to photons via this kind of coupling, then you can show that this guy induces the rotation of the polarization of CMB photons, and the angle of rotation is calculable. It's just the field distance times the anomaly coefficient times the gauge coupling of electromagnetism. Now, the reason why this is extremely exciting is because there is currently a hint that comes from reanalyzing Planck data, which points or kind of prefers a non-zero beta angle, and this is the work done by Komatsu and collaborators since 2020. And this is exciting, as I say, because if this is true, then this could be, if this signal is true and is generated by a light axion coupled to photons in this way, this would be completely excluding this kind of UV theories that you see in the screen. For the GATS, the weakly coupled heterotic string, and this I will discuss if I have time, perhaps also F-theory GATS.
Mario,
Mario,
can I
Yeah.
want to ask something also? Like, is it if this signal gets confirmed,
Yes.
is it clear that comes from an axion this way, or could it come
So,
from other things? And there is a way to determine whether it comes from the axion or not.
so first of all, well, I'm not an expert in this part of the cosmology and the analysis of Planck data and all this, but as far as I know, Planck was not originally designed for this kind of measurement. So this signal comes from a reanalysis of Planck data. Uh, Now, it could be dust. It can always be some systematic effects, but there is no standard model background, let's call it, that generates this kind of parity violating, if you want, interaction of CMB photons. It would be really something BSM-like, and the axion is perhaps the most plausible explanation. I don't think there is any other explanation from the top of my head, but maybe there is another one. People always talk about axion-induced cosmic birefringence. And I think hopefully within the next decade, we will know by the next generation observatories. But this, I'm also not sure. I will need to check.
Sorry, this is actually what I wanted to ask. Which which future experiments might see this?
think it's Simon's observatory. I forget about the exact name. It's
Simon's
one of these,
observatory. Yeah.
and one of these next generation CMB observatory. Yeah,
And I guess maybe you will talk about it later, but could I have situations where I have, I don't know, like a bunch of axions,
I will. I
and
will
then
talk
the
about.
effects cancel out? Okay, yeah.
Yeah. Yeah, so this was just the provocative, in some sense, or motivational statement for the rest of the talk. From the very beginning, let me just spend 30 seconds, 1 minute reviewing what I mean by action. What I mean by action is not necessarily the QCD action, is any kind of periodic or compact scalar field with this kind of shift symmetry. Now, as you know, in modern language, people typically talk about these guys as zero-form gauge fields. From the Fino side, most of the times this sounds like fancy language, but I will also give you an example which I think this audience knows very well, why this is not fancy language, is really informative and really gives you a lot of information about the involved physics. Now, this kind of shift symmetry is very important because it totally shapes the kind of interactions that we can have. We can have this kind of derivative couplings, topological interactions with gauge bosons or periodic potentials. And just as an example, as you know very well, in field theory, we have the very well-known case of the QCD action that comes after spontaneous breaking of the global Peccei-Quinn symmetry, which has a mixed anomaly with QCD. This anomaly is totally encoded in this coefficient, the anomaly coefficient, which is going to be a crucial quantity for the rest of the talk. Now, these days, many people, as you know, work in axion. So this is because they are very well motivated particles in BSM, and as you know very well, also arise quite easily in string compactifications, especially in the geometric regime. As I said, a prominent example, very famous example, is the case of the QCD axion, which solves dynamically the strong CP problem. And more generically, if you consider axion-like particles, they are very good dark matter candidates because they are naturally weakly coupled, they are stable, it's easy to produce them as cold relics, and they can, yeah, under some circumstances, they can even be dark energy if the potential is flat enough so that the mass is comparable to H naught, for example. Now, this was generic motivation for axions. In the context of this talk, I'm interested about axions because of the quantized or topological interactions that they have with gauge bosons. What I mean by this, to be very concrete, is that while the gauge coupling of electromagnetism, as you see here, or the decay constant, these are dynamical quantities that they are renormalized, they depend on the energy scale. On the other hand, the anomaly coefficient, as you know, is just an integer. This means that you can use, for example, anomaly matching arguments to show that once you fix it in the far UV, it remains constant in the IR. And this is what ultimately is going to allow you to directly probe the far UV just by doing IR measurements in a tabletop experiment or in cosmology, later in cosmology, or this kind of very low energy uh, measurements.
So Mario, can I ask something quickly?
Yes.
So if there's milli charges and stuff like that, then the A could be fractional. It's still quantized, but you don't know what the quantum is, right? Will that affect?
Uh, that is That is correct. Yeah, you need to know what is the minimal unit of charge
Right,
to then consider, like, you will realize that A, curly A is an integer in this unit. Yeah.
right. But is that gonna matter for what you will tell us?
It's not going to matter. But yeah, in fact, when I say here an integer, this is incorrect because this depends, for example, when I go to grand unified theories, this depends on the level of embedding, for example, of hypercharge into a gut. And this is typically a rational number. It's
Right.
the 5/3 that people typically consider. But whatever, the important point is that you can show that it doesn't run. Okay. And now is when this language of discussing actions as zero-form gauge fields becomes super useful because the fact that the phi, the decay constant, depends on the energy scale, but curly A is not affected by renormalization, is in one-to-one correspondence with the photon as a one-form gauge field where the gauge coupling runs, but the fact that the electron has an integer electric charge, has charge 1, or the neutrino is neutral, is not is independent of the energy scale. It doesn't depend on the energy, right? So for this reason, I believe that understanding axions as zero-form gauge fields is quite useful. Now, the main idea for this talk is going to be that the axion-photon coupling, because of these topological properties of axion couplings to gauge bosons, is going to be probably one of the best channels that we have to learn about UV physics, which is otherwise inaccessible. The energy scales that I'm going to talk about are going to be totally inaccessible to colliders or any kind of other experiments that we can perform. And this is thanks to the fact that axion couplings are topological. Now, all this was theory motivation. I think as a phenomenologist, one of the main motivations, in my opinion, for axions is the huge experimental program that we have trying to find this particle. You have in this map many names in different colors depending on the particle they are or they will search for. If you focus on the green, you will see many names in many countries. And one of the nice things, in addition to the large number of experiments, is also the diversity. There are very different experiments, such as, for example, alloscopes that look for actions that form part of the dark matter halo. This is the case of ADMX, for example. We also have light shining through a wall experiments, which is essentially you take a very intense laser, you point it to a wall, and now if there is a very strong magnetic field, there is a non-zero probability that a photon oscillates into an axion, goes through the wall, and then it oscillates back into a photon that you can detect. And finally, for example, we also have helioscopes like the proposed YAXO that aim to find for axions that are produced in the sun. Now, more focusing now on the axion-photon coupling or detection channel, we have this parameter space. We have GA gamma here in GeV inverse and the axion mass in electron volts. And we have a huge number of different constraints. The solid colors, the important only three features are important for this very busy plot. The first one is that the excluded region corresponds to the solid colors. The second is that we have a very well motivated target, and this is the QCD axion, which has a prediction given by this ratio. We have GA gamma over MA, given by very well known quantities, the gauge coupling of QED, and quantities associated to the chiral Lagrangian, like F pi and pi, times a mildly model-dependent quantity, which is this ratio of anomaly coefficients. Capital E is the mixed anomaly with electromagnetism, and N is the mixed anomaly with QCD. And that's why, since there is a model dependence for E over N, that's why this prediction is not a line, it's just a thin band here. Now, it is important to have goals. In this case, is the QCD axion. And the third important feature of this plot is this blue dashed line with the label alloscopes, which is the region that hopefully will be explored in a near future in planned and future experiments. Now, you can see that they will look for axions mainly to the left of the QCD band, hopefully also touching the QCD band. And this will become very important in the last or second part of this talk. So, as I said, let me be very optimistic. So we find an axion coupled to photons. We find a point in this parameter space. And the goal of the talk is to answer this question. What can we learn about the phi UV of the standard model? So the first thing we can ask is this question, which is the standard model unified in the phi UV? And by phi UV, I mean extremely high energies, like 10 to the 16, 10 to the 17 GeV. And by unified, I mean things like SU5, a gauge group based on SO10, a gauge group based on E6. That means that we take the 3-to-1 gauge group of the standard model, quantum chromodynamics and the electroweak interaction, and we embed it into a simple gauge group. Okay. So now the results I'm going to show you based on this paper are completely model independent. These results will not depend on the symmetry breaking pattern, on the GUT scale, what is the particular value of the GUT scale, and they will not depend on the gauge group, GGUT, as long as this assumption is satisfied. The assumption is that all the standard model generators, that is QCD and the electroweak interaction, has to come from the same simple non-abelian gauge group. This is the only assumption that I will make.
Mario, can I ask about the assumption? So the unification scale is supposed to be below the string scale. Could it be above the string scale?
Uh,
Like if they unify in some
yes,
sense above the string scale, do you count it as unification?
above the string scale.
Yes.
Well, I think I will
Imagine I
come
give
back
you a
to
model
this.
where I give some VEF, which is of order the string scale or something like that.
Yeah, I will get back to this later in the string part. If I don't answer your question, ask me again.
Okay, thanks.
Yeah. So just to remind you, the hints that we have for grand unification is, in my opinion, the best motivation that we have is precisely this question, which is why is the hydrogen atom neutral? Why is matter neutral, or why the proton charge perfectly balances or cancels the electric charge of the electron? I think it's fair to say that grand unified theories are the best explanation that we have to this answer. And there are also more technical questions, like, for example, we know very well that the standard model is a chiral gauge theory where gauge anomalies cancel. And as you know, this is a very non-trivial statement which can be very nicely explained, for example, in theories like SO10 or E6, which allow for complex or chiral representations while being always anomaly free. Finally, more phenomenological motivation comes from the extrapolation of gauge couplings, assuming 3 generations or the matter content of the MSSM, the prediction of the weak mixing angle, some relations between fermion masses. There is plenty of motivation for GATs, and this is what people have proposed. That's why people proposed these theories 50 years ago, and yeah, a lot of model building has been done in this direction. So what we have done here is to show that we can use the topological properties of axion couplings to gauge bosons. That is, we can use anomaly matching arguments together with gauge invariance of the full GAT theory, whatever is the gauge group, GGAT, in order to obtain very strong constraints for the couplings of axions, in particular the photon coupling, that can be tested in current, existing, and future experiments. Now, these arguments are based on topology, and this is going to make it very, let's say, model independent, at least with respect to the symmetry breaking pattern, as I said, or any kind of physics at intermediate scales. So what I have in mind in more detail is the following. We have a fully generic grand unified theory, GGAT, times a bunch of a non-specified number of global symmetries, U1 global, that I'm calling here U1 PQI, which commute, and this is very important, that commute with the gauge group. Now, let's assume for a second that these symmetries are exact up to the possibility of having a mixed anomaly with GGAT. So depending on the fermion charges, we can have different anomaly coefficients for each of the U1PQ symmetries. But at this point, you should stop and think about a similar situation in the case of the standard model, where we have baryon number and lepton number, both seem anomalous with respect to the weak interaction, but it is just an artifact because it's hidden in a basis rotation that you can go to B minus L and B plus L, and you realize that this symmetry B minus L is anomaly free, while this one is anomalous, has a mixed anomaly with SU2 weak. So it turns out you can always perform this kind of field redefinition, go to this basis where there is a single U1 that has a mixed anomaly with GGAT, a non-zero anomaly coefficient, and the rest are just anomaly-free global symmetries, which of course, if you break spontaneously, they are going to give you a Goldstone boson, a boson that is massless, only derivatively coupled, but crucially has zero anomaly coefficient with GGAT. And as I said, and now is when quantization becomes very important, the zero is going to remain zero to all energies. So whatever you do to your theory, you can have a very complicated symmetry breaking pattern. You can have different fermions that you integrate out, scalars, whatever at intermediate scales. The zero is going to remain zero and means that this Goldstone is never going to inherit a coupling to gauge bosons in the IR. So what this means is that putting things together, topology engaged invariance, is telling you that the linear combination, because in general, this U1PQ is going to be a complicated linear combination of the original symmetries. The axion which corresponds to the Goldstone boson of U1PQ is the only linear combination that couples to photons, and by gauge invariance, it also couples to gluons. So what this means is that A is going to get a potential from QCD, and the rest, the other actions that you have coming from this spontaneous breaking of these symmetries, are just going to be decoupled actions. They can have derivative couplings to fermions, for example, but these are shift symmetric. They are not going to induce an anomaly or this kind of topological interactions with photons. So the simplest case in which the U1 symmetries are completely exact has a very sharp prediction, which is there is a single axion coupled to photons, and this one is the QCD axion. So this means that you don't know where exactly, because I didn't say anything about the decay constant, but in the context of GATS, any action will live on top of the QCD band. Now, the moment you start doing model building on top of this, for example, you can start playing with axion mixing, which is ultimately related to generating shift symmetry breaking effects that mix these symmetries, or you can play with emergent actions very similar to pions in QCD. You can play with adding dark photons or things like orbifold GATS. Anything that you will do, anything that you will add, is having additional axion-like particles in addition to the QCD axion to the right of the QCD axion prediction. But the predictive power of grand unified theories is telling you that any region to the left is never populated by axion-like particles. So if you find an axion here in one of these future experiments well to the left of the QCD band, then you can be quite sure that in a model independent way, you are ruling out four-dimensional grand unified theories.
Maria, can I ask? I mean, it's a bit of a vague question, but there's like people have been discussing in quantum field theory this phenomenon of symmetric mass generation, where at strong coupling you can have sort of like couplings and things that you know they couldn't happen at with coupling. You can generate new terms that contribute to anomalies and stuff like that. When you give us this plot. And you say, you know, here are these things that in the end they don't change that. Which is the region which is compatible or not compatible.
Mm-hmm.
Did you think about all of that as well? I know it's vague, okay? So, you know.
I'm not sure what you mean by you mean some sort of a strong coupling?
Yeah. So maybe the gauge sec, you know, they are the gauge fields that we know and love, they are weakly
Yeah.
coupled, but as you go up in energies, there's like some other thing which is there's a strong coupling phenomenon, and then new fields appear or
Well, yeah. I mean, yeah, I'm not sure if I understand correctly the question, so my answer will be probably
no,
a little
I'm
bit
not sure if
vague also. But I will just say that, I mean, in the end, these couplings are topological. So I would imagine that you can also trust them if you go to strong coupling. These results. Relies
but I
only
mean,
on quantization of the anomaly coefficient.
but if in the UV, if as I go to strong coupling, there's many new like massless degrees of freedom, like fermions and stuff that appear. There can be more things.
But you can still do anomaly matching, no?
Yeah.
In That's all you require.
Right.
But yeah, I don't fully understand the
Okay.
framework
Thanks.
you
Then
have in
maybe.
mind.
Okay,
Yeah.
thanks.
But yeah,
Maybe,
good.
Ayo, maybe you can explain a bit because I remember you explained this to me once, but now I forgot. What is the intuition that you have to say that doesn't matter what you do, everything will go to the right, no?
Yeah,
In
so the
the
intuition
light
maybe is
actions.
clear after this example.
Okay.
So let's take this very simple example where we extend the one single action case in adding just another action that also couples to gauge bosons. And now we break the shift symmetry of the new axion by adding this bare mass term. Okay, I know this is not periodic and all this, but let's just do this simple exercise. Because of this term, you realize that the interaction eigenstates and the mass eigenstates do not coincide. So you need to rotate and go from one basis to another. And what this means is that one linear combination will be the QCD axion, the guy that solves the strong CP problem and couples to gluons, and the orthogonal linear combination is going to be what I call the ALP. Now, because these interaction and mass eigenstates do not coincide, the ALP is also going to get a mixing induced coupling to photons. Now, because it's mixing induced, the effective coupling of the ALP, coupling to photons, is going to be bounded by the original coupling. And this is just because you're paying the price of a mixing angle of the ALP with the QCD axion, and the QCD axion is what really couples to gauge bosons. So this mixing angle price, for example, if you go to the very light regime to MB over NQCD much smaller than 1, the mixing angle, because these are scalar fields, is going to depend as MB square over NQCD square. So the effective coupling of the ALP is going to be GA gamma ALP here is going to be MB square over NQCD square times the coupling of the QCD axion. And this is what generates this behavior. And by brute force, what you can see is that if you scan in all these parameters, you scan in the mass of the ALP, you scan with on the FA and FB decay constants, what you generate, any additional axion-like particle in addition to the QCD axion, always lies to the right of the QCD band. So even by brute force, you see that you never have axion-like particles above the QCD line. This is just a property of orthogonal matrices, if you want, that you use to go from one basis to another. And that's why it also does not depend on the number of axions.
And Mario, what happens if the mass is bigger
Oh,
than...
if MB is much bigger than the QCD axion mass, you just integrate out B, and at low energies, what you have is well below the mass of the MB. What you have is A is going to give you the main contribution to the QCD axion. So the MB much bigger, much heavier, let's say, than NQCD is when an axion-like particle is, let's say, here, and the axion, QCD axion is here. Is that a bit more clear?
Yeah.
Okay, good. So this was just one example that by adding axion mixing, mass mixing or kinetic mixing, you will never populate any region to the left. Good. So I'm quite behind the schedule, but it's okay. This part I think I can go faster because you know much more than me on these topics. So I also promised to say that actions can say also something about string theory, and this is based on these two papers plus ongoing work that I'm doing with Timo and Michael Nee. And yeah, this is the motivational slide that I think I don't need to emphasize a lot to this audience. But yeah, it's fair to say that probably the best understood framework unifying GR and particle physics that we have is given by string theory. And in the context of this talk, what I believe is quite interesting from the Fino point of view is that at least in the geometric regime, axions appear to be a quite generic prediction of string compactification. So how do stringy axions look like? As you know very well, we have extra dimensions and we have higher form fields that we can integrate over cycles in the compact space. So essentially, when we take, for example, a p-form field and we integrate it over a p-cycle, what we get in the 4D EFT is a perturbatively massless Goldstone that has only derivative couplings. And of course, it's not going to be massless after all, but unlike field theory, where in principle there could be local operators breaking the shift symmetry of theta, here, because the axion secretly comes from a higher form field, the shift symmetry breaking effects that we generate are going to be exponentially suppressed. So it turns out that all this is very nicely explained by global higher force symmetries. And what you find is that the potential that you can generate is going to come with this kind of exponential separations where the action, instant on action S, is typically much larger than 1 when cycles are considerably large. From the Fino point of view, what makes all this very exciting also is that people realize that the number of actions is in one-to-one correspondence to the complexity to the number of inequivalent cycles in the compact space. And this has led to the so-called string axiverse, which, especially in the last decade or so, has attracted a lot of attention also from phenomenologists and people working on cosmology and astroparticle physics. So to give you a little bit of context about what other people have done, uh, this is, for example, the case of the type 2b axiverse, where there has been a lot of effort, especially by the Cornell group, but also here in Europe by groups led by Michele or by Alexander Westphal-Indesi, Arthur Hebeker. Many people have worked on these kind of constructions, and mainly, if not always, using some a concrete type of compactification, which is orientifolds of Calabi-Yau threefolds. So just to give you very quickly an example, this is a very nice paper by Naomi and collaborators where they consider the axiverse in a class of theories considering Calabi-Yau threefolds where gauge sectors come from wrapping D7 branes over 4 cycles. In this case, the integer that tells you how many axions you have is one of these Hodge numbers, H11, that counts the number of inequivalent 4 cycles around which you can integrate the 4 form. And yeah, what they have done is using this software, this package, CY Tools, which I believe is something that has pushed a lot the field because it really allows you to do quantitative studies of the axiverse. What they have done is this kind of work where, for example, for this type to be axiverse, they are able to compute for different H11s what is the expected coupling to photons. So here what you see is 2 different scenarios. You see a non-GAT symmetric case and a GAT symmetric case. And what they do is for every axion, they compute what is the expected coupling to photons and they plot it. And this is the same plane as before, GA gamma versus the axion mass. And in this plot, if we focus in the GAT symmetric case, there are 2 nice, or let's say 2 well-defined patterns. The first one is the larger is H11, the heavier is going to be the QCD axion. This is quite easy or intuitive to understand, and this is because the larger is H11, the more complex is the compact space, the larger is the volume. As the volume grows, the string scale comes down, and as the string scale comes down, also the decay constant of closed string axions is going to go down, which pushes the QCD axion mass. Now, any axion which is not a QCD axion and lies to the right of the QCD band is going to get a mixing induced coupling to photons, and this mixing induced coupling decreases as the compact space becomes more complex. And this is what you see in these colors here, where red, which corresponds to H1150, is above the dots associated to this green or bluish, and is larger than the yellow, larger than the purple. There are, of course, few points or dots here that correspond to the axions, I believe, correspond to the axions that, as we were discussing before, are, let's say, heavier than the QCD axion mass, and you kind of integrate them out. Yeah, something else you can also do is related to this project I've done with the Berkeley group, where you can generate a large ensemble of compactifications using CY tools, and you can ask what is the QCD axion mass and QCD axion decay constant for each of these compactifications for the different H11s. And now you can impose an additional condition, which is, let's assume that we want to keep field theoretic unification. In this case, we need to impose the string scale is above the GAT scale, and this limits how low the total volume can go, which limits how low or high, in this case high, the decay constant can go. What happens in the end is that you can kind of get a well-defined range for the possible QCD axion masses, assuming that you want to keep field theoretic unification in the context of type 2b, and this is something which is very useful for the experiment. Now, I said that this kind of software, CY Tools, is really a game changer.
Mario, I
Yes.
just have a quick question on the previous plot. So, going to say, yeah. So, how many of these models here have like stabilized moduli?
This is related to this slide, which is one of the current limitations of this kind of analysis. I thought,
Okay.
yes, moduli stabilization or getting the right, let's say, particle content, like getting the standard model out of it, is something that in this analysis is always postponed. Okay, so this uh, software is extremely good at giving you this kind of quantities, but things like modular stabilization or uh, gate sectors and all this is something which is not considered because otherwise that would be much harder. So this is, as I said, the list of limitations that currently we have. First of all, we don't know if we are looking under a lamppost because this is focused on these kind of studies are focused on this kind of oriented faults of Calabi-Yau 3 faults. There is no modular stabilization implemented. There is no uh, understanding of possible additional gate sectors that could couple to all these actions and could totally change the masses and all the patterns that we observe. But still, understanding these limitations and, for example, understanding if they have an impact in cosmology, for example, if you make the actions heavier and can now more efficiently decay into degrees of freedom of the standard model, is something that is also very exciting and is something I'm doing with Josh, Katie, and Ben. So, yeah, this was related to type 2b, but as the title of the talk says, this is not what I promised. So let me just, in the last part of the talk, focus on the heterotic axiverse. This is a name coined by this paper, which I think is an extremely good one. So the things that I will say now are contained in these two projects that I've done, as I said, with Pratik and Mick, and also with Timo. And it's just going to be a very simple observation, and is that in the context of heterotic strings, in particular EA cross E8, which is the one that I will focus, because anything that I will say for EA cross E8 is also going to be true for the heterotic SO32 or for type 1, is extremely important for axion physics in the IR that the gauge group is fixed by anomaly cancellation. And this, as I will show you now, because this mechanism of anomaly cancellation is in one-to-one relation with axion couplings, this actually allows you to get very well-defined predictions in the IR that you can test in the experiment. Yeah, to this audience, I don't think I need to introduce or go into details, but again, I will spend 30 seconds. I just want to say that, as you know very well, the heterotic string is a theory of closed superstrings in 10 dimensions, and the effective action is given by 10D n equal 1 supergravity. So we have the gravity supermultiplet with metric and moduli fields, the B field, which is the most important character because it's the source of actions in this theory, the dilaton fixing the string coupling, plus the Yang-Mills supermultiplet that gives us charged matter in the 4D EFT. Now, as I said before, the anomaly cancellation mechanism, the Grinchbars mechanism, that also not only fixes the gauge group, okay, it also is extremely important for actions because, as you know, when you take this kind of TEM form and you integrate it over a six-dimensional space, what you necessarily get in the 4D EFT is an axion coupled to gauge bosons. So if you want to cancel anomalies in the 10D theory, and unless you remove this action by fluxes or things like that, making it much heavier, you expect to have a light degree of freedom coupled to gauge bosons in the 4D EFT. Now, we seem to have a problem because there is of course, the theory is very simple at the 10D level, but it can become very complex in the 4D EFT sense. And this is because we are compactifying in a six-dimensional space. So we have a lot of freedom to choose which compactification or which compact space we want. We can turn on things like discrete Wilson lines. We can turn on fluxes. In this way, many four-dimensional EFTs become available. We can have things that look like a God, but we can also have things that do not look like a unified theory. We can even get only the standard model gauge group, for example. So one could think that every statement that we can make for axion physics is going to be lost in all this complexity that we have from the 4D point of view. But the point, and that's when anomaly matching and the fact that axion couplings are topological and quantized becomes important again. You can show, for example, matching the mixed anomalies between the global higher force symmetries from 10D to the 4D axion shift symmetries to the anomalies of the axion shift symmetry in 4D. And you can show that literally you can match the couplings from 10D to 4D in such a way that the results, the axion couplings, only depend on how you take the standard model gauge group and you embed it into E8 cross E8. So this sounds very vague, but the strategy is going to be the following that I will show you now. The strategy is take the 10D couplings, match them to the four-dimensional EFT at the compactification scale, and since you know they are topological, they will not change as you go very low in energies. And the prediction that the perturbative heterotic string is going to give you is that the coupling to mass ratio, GA gamma over the axion mass for any axion in the heterotic string is going to be bounded by this quantity, which is the prediction of the QCD axion. Okay, so this is the result. And now let's see how to get it. Yeah, so in the heterotic string, as I said, the most important character for axion physics is the B field and the 10-dimensional dual, which is this B6, a six-form field. And this tells you why you have two qualitatively different kind of axions in the heterotic string, the so-called model-independent axion, which is the integral of B6 over the entire compact space. And it's called model-independent because the properties are totally independent of the compact manifold in the sense that the decay constant is fixed and the coupling to gauge bosons, for example, is also fixed, and in particular is fixed from or by the Bianchi identity for the field strength of B, for the B field. On the other hand, the model-dependent axions, as the name says, is a little bit more model-dependent. And this is because even the number of these guys depends on how many two cycles we have. That is, it depends on the compact space. The decay constant is also a little bit model dependent, even though you can get lower bounds of this form as detailed in Sverchek and Witten. But the most important part is that while the decay constant and the number of these guys depends on the compact space, the couplings to gauge bosons are going to be quite independent. And this is because they come from the Green-Schwarz counter term that you necessarily need to have in 10 dimensions. Yeah, I'm running out of time, but yeah, so I will just go. So essentially, the strategy, as I said, is to take the 10D couplings, for example, in particular, take the Green-Schwarz counter term, and after you write the explicit form of this 8 form that you use for anomaly cancellation and you integrate over the compact space, you will get the 4D axion EFT at the compactification scale. Here I have separated, as before, the model independent from the model dependent axions. So we have the coupling of A, model independent axions, as I said, universally coupled to all the gauge bosons, because this is just compact notation. Trace 1 F square corresponds to all the unbroken 4D gauge groups from the first D8, and trace 2 F squared corresponds to the gauge bosons that survives in the 4D EFT that come from the second D8. Now, fine, this one is universally coupled. The model-dependent axions, on the other hand, as I said, have a mild model dependence, and the model dependence here comes because they have each of the BIs has a calculable anomaly coefficient, this Ki1 and Ki2, that depend on the model. So you could think that all the predictivity is lost because of this fact, but the important point is that each of the BIs individually couples to the entire trace 1 f squared or to the entire trace 2 f squared. And this is crucial because what this tells you is that when you put everything together, the most generic situation is a situation in which we have a linear combination that I call theta 1 coupled to trace 1 f squared, and in principle a different linear combination, not necessarily orthogonal, theta 2 coupled to trace 2 f squared. So independent of how complicated are these linear combinations, we know we only have two, theta 1 and theta 2 coupled to gauge bosons, with all the orthogonal linear combinations completely decoupled from gauge bosons. This is crucial because, as I said, what this is telling you, what this is suggesting, is that the IR couplings well below the compactification scale are just going to depend on how you take the 3-to-1 gauge symmetry of the standard model and you embed it into the 10-dimensional gauge group. And now, instead of a huge, broad range of possibilities, we only have two options. Either we take the standard approach, we take the standard model, we put it into a SU5, E6 subgroup or whatever subgroup of E8, leaving the second as a hidden sector, or we take the standard model and we have a non-trivial embedding of the 3-to-1 gauge symmetry of the standard model into E8 cross E8. So these are the two options that we have. So let's start with the simplest, which is the standard approach to phenomenology. We take the 3-to-1 of the standard model, we put it into the first E8, and we leave the second as a hidden sector. Then you automatically see that theta 2 is not coupled to gauge bosons of the standard model via the anomaly. It is only gravitationally coupled to us or via mixing with theta 1. The only guy that couples to gauge bosons of the standard model, in particular to photons, via the anomaly, is going to be theta 1. And this is crucial because then this is very much like the case of a four-dimensional grand unified theory that I discussed before. And just exporting those results to this case, we automatically understand that finding something like cosmic birefringence or ultralight axion coupled to photons is going to be well to the left of the QCD band, and therefore it's going to be incompatible with the heterotic string with the standard embedding of the standard model into E8 cross E8. If you want to phrase it in this way, any axion, be it the QCD axion or a fully generic axion-like particle, in the case of heterotic string with a standard embedding, has to satisfy this bound for the coupling to mass ratio. And this is, I emphasize, the same bound as for four-dimensional GATs, even if there was never a phase in 4 dimensions where the standard model is unified. And this is, again, independent of the choice of compact space or how we obtain the standard model spectrum from the E8 cross E8 heterotic string. Now, as I said, this is not the only option that we have. We can also do a non-standard embedding of the standard model gauge symmetry into E8 cross E8. This is what we have, Timo and I have explored recently in this paper, and is to follow up on this early paper by Timo and collaborators, take the standard model hypercharge, and now embed it non-trivially into both E8s. In this way, what you are doing, morally what you're doing, is to take part of electromagnetism and put it into the first E8 and into the second E8. Assuming that QCD and the electroweak SU2 sector comes only from the first E8, then theta 1 is going to be something like a QCD axion because it couples to gluons. But theta 2 can couple to photons via the anomaly because part of electromagnetism is also embedded here. So now the question is, how light can theta 2 be? So the first thing that you realize is that there are some conditions that theta 2 has to satisfy. That this kind of model has to satisfy in order for theta 2 to be a very light axion-like particle. The first one is that you want to remove every confining interaction from the second E8, because if not, if there is some sector that confines in the second E8, then this will make theta 2 very heavy. The second is that you want to remove every chiral fermion from gauginos coming from the second E8, because if there was some chiral fermion from these gauginos, then it would have electric charge, and then you are ruled out from experiments. And finally, we have also measured the gauge couplings and the weak mixing angle at around the TeV scale and weak scale very precisely. So you want to make sure that you get the right low energy values for the gauge couplings. And in particular, this is going to be the most non-trivial condition to satisfy. So the models we have considered is following up in the early paper, is to consider line bundle models where you can completely remove every non-abelian sector in the second E8 and obtain hypercharge as a linear combination of the U1 in the first E8 and one or more of the U1s in the second E8. This can be done quite easily. What is less trivial is to satisfy, as I said, the condition of getting the right value for the low energy gauge couplings. And this is because the moment you put non-trivially hypercharge into both E8s, you have this kind of non-trivial matching condition where the first, which is telling you that the value of the gauge coupling for hypercharge at the compactification scale has a contribution from the first E8, which is like this, the standard gap prediction, plus at tree level, plus a contribution from the second E8, 1 over alpha gap. In addition, the moment you turn on line bundles, you also introduce holomorphic threshold corrections that are gonna create an entire mess because they will introduce further corrections to the gauge couplings. So this is the condition that you need to satisfy. You want to somehow balance the tree-level contribution from the second D8 with this holomorphic threshold correction, delta Y. Because if not, the model will be already excluded. But assuming you can do it, and assuming you can construct this model where every non-abelian sector in the second D8 is removed, then you can ask how light is theta 2. Theta 2 is always going to get a potential because we know that it cannot be a flat direction, it cannot be an exact global symmetry. Then what you realize is that there are UV gauge instantons in the second D8 of this inducing a potential of this form. There is a UV scale as usual times an exponential suppression. The nice thing is that this framework allows you to compute the UV instanton action as a function of the threshold corrections and the tree-level contribution to the gauge coupling. So what we find is that imposing that we get the right values for the IR gauge couplings, plus we remain in the perturbative regime where this threshold correction delta hat 0 is much smaller than the tree-level contribution, then what you find is that the UV instanton action is order 1. Since this instanton action is order 1, you automatically find that the ALP is heavy because of this kind of potential. And because it's heavy, then the ratio GA gamma over M is small. When this ratio is small, what this means is that this axion-like particle theta 2 is going to be well to the right of the QCD band. So this is just a very busy plot, but I'm running out of time. So I will just say that what we find, you can go to the paper for more details, is that assuming that the one loop contribution is less than around 75% or so of the tree-level contribution, it is not possible to populate regions to the left of the QCD band. The QCD line here corresponds to the black line. So as long as you are perturbative, in the sense that one loop corrections are smaller than the tree-level contribution, you do not expect axion-like particles to the left of this solid black line, even in the case of a non-standard embedding into the E8 cross E8 group. This is just something I prepared about this work in progress with also with Timo and Michael Nee about actions in F-theory GATS. I will not enter into details because I have only a couple of minutes. I will just say that the results are quite similar in the sense that it is possible to show that even in the presence of holomorphic corrections to the gauge kinetic function, as long as the gauge couplings approximately unify around the string scale or compactification scale, then every axion-like particle which is not the QCD axion is going to be heavy. So just to conclude, let me show you this final slide with I believe, the lessons that we can learn from this. The first one is that, of course, finding out about dark matter or whether if we find an axion, whether it solves or not the strong CP problem are extremely important and interesting questions. I think it is also important to emphasize that axions are unique because they can offer, unlike any other particle almost, they can offer very valuable information about the far UV limit of the standard model. Especially this is exciting because of the huge experimental program, as I said, trying to find this particle. Most of the experiments are going to search for axions to the left of the band. So you could think they are not well motivated or they are in some sense not looking in the right region. I think it's important to reach the QCD band, but also it's interesting to search, very interesting to search to the left, because it is precisely this kind of action to the left of the QCD band what can give you lots of information about the far UV of the standard model. Finally, what I also want to emphasize is that we cannot confirm, I don't want to say that we can confirm grand unified theories or the heterotic string by finding an axiom, but I think it's quite remarkable that actions can offer very non-trivial tests to these theories. Thank you.